Let's go over the language of quantum mechanics, which is some really beautiful mathematics. This video is inspired by my favorite quantum mechanics book, Principle of Quantum Mechanics by Shankar. Okay, well, let's start off with what is a linear vector space. So it's simply a collection of objects which are known as vectors. In this video, we're going to be moving away from the notion of a vector simply being an arrow with a direction and a magnitude. All of the rules of vectors tend to be satisfied by loads of different other objects such as functions, etc. Now, a linear vector space is a collection of these vectors, and we tend to denote them with this bracket notation across here. So for instance, this one here, the first vector, is denoted with just essentially a little line, then a little pointy bit at the end. And this notation was invented by Paul Dirac for quantum mechanics. We'll explain that later. But for now, just think of it as a regular vector. This one here, number 2, number 3, and some general, there's vector v and vector w. Now, there are a few things that need to exist in order for the collection of objects to be a vector space. Now, number 1, there needs to be a definite rule for additions. And in other words, there has to be a rule for essentially adding those two vectors. There also needs to be a rule for multiplication by scalars. So if I was to multiply any of those vectors by some scalar, call it alpha, well, then this will also be possible. If we were to add two vectors, so let's say we add this one plus this one, the result will be another vector which will also be part of that vector space. And we tend to denote the vector space just by this mathematical notation. Just like regular vectors, multiplication by a scalar needs to be distributive. Now, what does that mean? So alpha, if this is multiplying v plus w, well, this will just simply be equal to alpha times one of the vectors plus alpha times the other vector. This will also be a collection or an object from the same vector space. This vector space needs to also be distributive within the scalars themselves. So let's say we have two scalars, alpha and beta, and let's say that they multiply this vector v. Well, this will simply be equal to alpha times v plus beta, which is the other scalar, multiplied by the vector v. So far, nothing too different. Additionally, multiplication will work in a similar way. So alpha times b times this vector should be equal to beta times alpha times the same vector. Some other rules that kind of make sense from algebra is that v plus w will of course have to be equal to w plus v, and additionally they also have to be associative, meaning that v plus brackets w plus z will be equal to v plus w brackets plus z. Now the next one is pretty important, and there needs to exist a null vector. And shall I just write this with words that a null vector exists such that vector v plus, let's call that null vector just 0, will be just equal to v. Additionally, the final condition for a vector space to be a vector space is that there needs to be an inverse operation to every operation. So if for instance, if you were to take v, you could take away v, and the result will simply be the null vector. Now, while all of these rules here will hold true for something like an arrow, which is being added up in 2 or 3 dimensional space, they will also hold up for other objects. For instance, you could have, I don't know, something like the set of 2 by 2 matrices that will essentially follow those rules. You can also have the set of functions or sets of functions, linear functions, that obey those rules, that, let's say, f of x plus g is actually equal to f of x plus f of g, that alpha times beta times f of g is equal to beta times alpha times f of g, etc. So a vector space is a collection of objects which are not necessarily arrows. And now let's have a look at a critical definition for quantum mechanics and for what, well, essentially what a dimension is, and that is linear independence. A set of vectors is said to be linearly dependent if there is a non-trivial linear combination of the vectors that equals the zero vector. Now in this case, non-trivial simply means that we're ignoring anything that is being multiplied by a scalar of 0 or by the zero vector. If no such linear combination exists, then the vectors are said to be linearly independent. So let's just illustrate this with some arrows in 2 dimensions. I have one vector here which has a magnitude of 2 and it's pointing to the left, and one vector here that has a magnitude of 1 that is pointing to the right. I could multiply this blue vector by a scalar, which is 2, and I'm going to get exactly the same vector as this one, but in the opposite direction. And I could add them up, and what I would get is 2 minus 2, which will give me 0. So those 2 vectors are linearly dependent. However, if I have one vector which is purely in the horizontal direction, so let's say across here, it has a length, I don't know, L, then I have another vector which is purely in the vertical direction. So let's make that angle 90, and let's put that one over here, and it has another length, let's just call that D. There is no combination that I can have that will make the sum of those 2 vectors equal to 0, and this means that the vector D and the vector L are linearly independent. And mathematically, for some vectors, so let's say that we have vector 1, we have vector 2, and overall we have n vectors. They're going to be linearly dependent if we can add those up. And shall we just call the vectors I, and there exist some scalar coefficients, let's call them alpha I, such that when we add them up and we're summing from I is equal to 1 to I is equal to n, that we actually get the 0 vector. Well, let's illustrate this with an example. We have a couple of column vectors, well, 3 column vectors here. Are those linearly independent? Well, let's see if we can get them to give us the 0 vector. So what I'm going to do is I'm going to multiply the first one by 2, then I'm going to get essentially 2 to 0, and then I'm just going to add them up with 1, 0, 1, so the coefficient of this one will just be 1. Now I'm going to have 3 overall here on the left, which means that if I take away this vector here, I'm going to get some zeros, so I'm going to give the coefficient of this one to be negative 1. Well, if that's the case, what I will essentially get is 2, 2, 0 plus 1, 0, 1, and then take away 3, 2, 1, which will give me a vector which will have the following components. So 2 plus 1 minus 3, that will be a 0. 2 plus 0 minus 2, that will be a 0. And then 0 plus 1 minus 1 will just give me a 0. So there exists some coefficients which are just 2, 1, and negative 1, so that I get the 0 vector. Therefore, those vectors are linearly dependent. And just a little note that there is a mathematical trick with determinants, and that every time we want to check whether some vectors are linearly independent, this would mean that if we were to write them in a matrix in a column, for instance, what we wanted to do is check that 1, 1, 0, 1, 0, 1, and 3, 2, 1 were linearly dependent. So all I've done here is I've put them in a matrix right across here, and I found the determinant of that using the standard linear algebra rules for finding the determinant, and we get a result of 0. And if the determinant is equal to 0, this means that its columns are linearly dependent. So I'm going to say that this means here that they are linearly dependent. So the concept of linear independence is crucial to the idea of dimensions. For instance, a vector space is n-dimensional if it has a maximum of n linearly independent vectors. If that's the case, we typically tend to denote it, let me just write this properly, like this, so where n is the number of dimensions. Now, let's have a look at an example of, let's say, a 4-dimensional space. So typically we use the 3 dimensions, but let's say that we take the space of 2 by 2 matrices. So we can have one vector which could be given by, let's say, 1, 0, 0. We can have our second vector to be equal to 0, 1, 0, 0. We can have our third vector to be, well, we get the idea, 0, 0, 1, 0. And our fourth vector, in this case, will simply be 0, 0, 0, 1. And another really important theorem states that a set of n linearly independent vectors in an n-dimensional vector space is actually called a basis. So in the case of 2D matrices up here, those are our basis vectors. But in general, if we have a vector, let's call that very imaginatively V, we can express that as a sum of the components Vi that are multiplying all of the individual basis vectors. And this is of course summed from I is equal to 1 all the way to n for an n-dimensional vector space, whereas this coefficient here is just known as the component. So one of the most useful areas of classical physics is the dot product for three-dimensional vectors. Just as a reminder, the dot product between two vectors, let's say we have an arrow E and then we want to dot it with an arrow B, is equal to the sum of all of their components multiplied. So it's going to be AX times BX plus AY times BY plus AZ times bz. And this is essentially the dot product, which is a scalar. Now, we're going to want to generalize this idea and come up with a rule of finding the product, or what we call the inner product, not just for three-dimensional arrows, but for complex vectors such as v and w, etc. Now, the first thing that we need to introduce is the symbol for that. So the inner product between v and w is actually given by the following symbol, like so, in bracket notation. So this here is the inner product. There are three very important axioms that we're going to be using for the inner product. Now, the first one is that if we were to swap the order of the operations, what we're going to get is the complex conjugate of the original operation. And this is super important because the inner product is sensitive to order, unlike the standard dot product when we're dealing with arrows. The inner product of a vector of itself will either be 0, and that's only if we're dealing with the 0 vector, or it will be greater than 0, so pretty similar to arrows. And finally is that it's just a linear operation. So this means that I can take away this coefficient outside of the inner product and just calculate the inner product of this vector and this vector, and same with this part of the equation. And we're also going to say that two vectors are orthogonal if their inner product is indeed equal to 0. Now, the norm of the vector is simply defined as the inner product of the vector with itself, square rooted, and you're going to see this written with this notation. So let's actually obtain an expression for the inner product. If we have two vectors, v and w, the inner product of v and w will be equal to the sum of the components. So we're going to be summing twice, first over I to n, from I is equal to 1 to n, and then across j to n of the transpose complex conjugate of vi, which we're going to denote with this star. This will be important because, as we said, this is an operation in which the order actually matters, multiplied by wj, and then we're going to need to find the inner product of the basis vectors, so I and j. Now, for simplicity, or well, this is actually the way I would say virtually most of the calculations are done. The inner product of the basis vectors will be either 1 if I is equal to j, or 0 if I is not equal to j. Mathematically, we tend to represent this with a function which is known as the Kronecker delta function, but that's just as a little aside. So assuming that this is equal to 1 and we're dealing with orthogonal basis vectors, that their inner product is 1 if the indices match up, this will be equal to the sum only across the I index to the nth dimension of the transpose complex conjugate of vi, and then wi, and then the inner product is just 1. So this here, I've just seen this here should be a v, please excuse that, but the inner product of v and w is equal to this expression. Now, what is actually the transpose conjugate? Let's imagine that we have a vector. So we start off with a column vector. I don't know, let's have 1 and then 1 plus I across here. So just a two-dimensional one. So our what is known as a bra vector, which we're going to introduce in a moment, will be equal to the transpose. If this was a column vector, we're gonna swap this for a row, and this will have elements of 1 and then 1 minus I, because it's the transpose conjugate. So for the transpose bit, we have swapped the rows to a column. So shall we just write that? So swapped rows for columns. And then the other thing that we've done is that we found the complex conjugate of all the elements inside. Now, why do we actually do this? If we have two column vectors, we cannot directly apply matrix multiplication. And because linear algebra, in a way, is the language of quantum mechanics, or it's very heavily used in quantum mechanics, then what we can do is we can turn one of those column vectors into a row vector, and then we'll be able to multiply using our standard row by column rule for multiplying matrices to produce a number out. Now let's have a look at the expansion of vectors in an orthonormal basis. So we have this vector v, and what I want to do is find the jth component. This could be any number. Now all I really need to do is just take the inner product with the unit orthonormal vector j, and what I'm going to get is really just the sum from I is equal to 1 to n of the coefficients, and then the inner product between j and I. Now this is of course only equal to 1 if I is equal to j. So what this will do actually is just give me the jth coefficient of that component of the vector. Okay guys, we're gonna stop there for now. If you're interested in having a look at another quantum mechanics video, have a look over there. Also let me know in the comments if this style of videos is something that you enjoy and you want to learn more about. Thank you very much.